So we had started the discussion on entropy in the previous week. So S is going to be basically standing for entropy. In a sense, when you're going to be looking at entropy, entropy is basically going to be the amount of freedom experienced by a particular object you can imagine, or whatever system which you are considering there. So when you're going to be considering freedom, I think we have already discussed this. Freedom basically talks about, there are many different ways of looking at freedom here. The more randomness the molecules or the atoms of a particular species are experiencing, the more freedom they are going to be experiencing, the greater the entropy. Another way to look at it is, you can look at it as the more different states. Let's say I'm going to be having a particular gas taken. Okay, if that gas is going to be having, say, entropy being a particular value, what does that really mean? How do I get that number out? What does that number really signify there? There's two more ways of looking at it. One way I would have discussed in the previous class, which is the number of different accounts into which the system can park its energy into. The various different accounts in which it can park the energy, that is going to be the number of different accounts, basically tells us how much freedom the molecules are experiencing. Another way to look at it over here is going to be a more pure statistical way. This is going to go like this. The gas over here at that particular system has some energy associated with it. So this energy is basically going to be something which is now going to be distributed to those gas molecules in some way or another. That distribution of gas molecules is going to be having some probability associated with it. So how many other distributions are possible for the same energy? The greater the number of distributions possible for that particular same energy, then the greater the entropy. So the energy here is going to be something which is going to be distributed among the particles of the system. Now when I say among the particles of the system, I am talking about going as deep down as possible. Meaning it is going to be something which is effectively distributed among the various quantum states. Think of it as quantum applicable states. Whatever applicable states are there, you are going to be having the energy being distributed into that. So the many different ways in which this distribution can happen is ultimately what is going to be called as the entropy of that system. How many different ways this distribution can happen, the greater the number of ways in which the distribution can happen, the greater the entropy of the system. That is basically another way of looking at it. So greater the number of ways this distribution is allowed, implies greater the entropy. So effectively the number of different ways in which we can represent that particular energy spread between the molecules or particles of the system basically decide its entropy. Now these are three different ways of looking at entropy. Now why did I discuss each of these three ways? Mainly because in certain higher level of questions, different understanding will help you solve the question faster. Especially when it comes to new models of questions which you might find. Newer models of questions, if you have a more clearer and different understanding of what the same thing means, it will be much more easier to basically proceed in and solve it off. Okay, now in the previous class, I think we had started discussing entropy formula for different types of processes. So delta S was Q reversible by T, and this was the formula we had started applying from there. From this on, I think we had started going into delta S for most of the standard processes. Constant volume process, we ended up having it as Q reversible by T. Now if it is going to be at a constant volume, any particular process, Q reversible is the same as QV. Why? Because QV is going to be a state function. So it behaves like a state function. So we are going to be simply having it as QV by T, meaning QV can be written as, of course, NCV dt by T. meaning we are going to be having this effectively working out as an integral of this over T1 to T2. So we are going to be having it as NCP ln T2 by T1. Sorry, CP in potte na, sorry. NCV ln T2 by T1. So this is going to be my delta S for any constant volume kind of process. If I was going to be having delta S for a constant pressure process, same kind of logic applies. We'll end up having it as T1 to T2. It is going to be NCP dt by T. Why? Because QP works out as a state function. State function implies same for reversible or irreversible. That's the idea here. Because it's a state function, what is the advantage? It is going to be same for either an irreversible process or a reversible process. I do not really care. What do I mean here? As long as the process is going to be something which is happening at a constant volume or at a constant pressure. If it is an irreversible process also, no problem. Because the Q reversible will be equal to the same as the Q irreversible which you have got as QV there. Because QV behaves like a state function. So in this particular case here, the idea here is if it's a state function, reversible and irreversible path have same QV. That is the idea here. So as long as you are given QV for any one of those paths which you know for, automatically you can use it for the reversible path as well. Same application is applicable for the QP also. So effectively we end up having this as NCP ln of T2 by T1. Now this advantage is basically going to be straight away not needed as long as it's going to be something which is going to be a phase change type of process. We had seen that also in the previous class. So if I'm considering any delta S for a phase change type of system. Now phase change over here means anything like this. You can have fusion, vaporization, you can have sublimation, you can have allotropic change.
So what's allotropic change?
Allotropic change, na, let's say I'm going to be having sulfur rhombic. You have not done group 16 yet, na? I'll use some other example. Let's say I'm having carbon diamond or the carbon graphite.
Oh, sorry. Okay, I thought, okay, got it, sir. Like changing diamond to graphite to diamond.
Yeah, so
I just forgot the term allotrope.
Yeah, cool, huh? So when you're going to be having carbon graphite being changed into carbon diamond or rhombic sulfur changed into monoclinic sulfur, you end up having that being an allotropic change, meaning the crystalline structure internally is changing, and that change is basically going to be mentioned as allotropic change. So one of the advantages is each of these things over here are going to be happening at equilibrium. In the sense, you're going to be having the phase change itself being a reversible phase change. So for instance, if I'm looking at fusion, we can talk about it as solid melts to become a liquid. So for water, we all know at 1 atmosphere pressure that this is going to be happening at 0 degrees Celsius or 273 Kelvin. So temperature of fusion is going to be known. Enthalpy of fusion we can calculate over here. The enthalpy of fusion is something which we can directly calculate. If I'm going to be putting a not condition, it will not be correct because in this particular case this is happening not at yeah. So can you hear me still? Am I audible?
Yes, sir.
Okay. So in this case here, we do not put a delta H naught over there, mainly because not condition means standard conditions. In this case, it's not necessarily standard. It is going to be the temperature at which the allotropic change or whatever phase change is happening over there. So this delta H of fusion is directly going to be Q reversible for this case over here. So we can straight away use delta S of phase change equal to delta H of phase change divided by temperature of phase change. As simple as that. So you can have it as delta H of phase change by temperature of phase change, which straight away gives us enough substance over there. Next up, when you're going to be having a process which is going to be a random process, Alright, something where it is not necessarily going to be reversible or anything of that sort, a random process where I'm having it going from state S1 to state S2. So let's define state S1 first. We are going to be having P1, V1, T1, P2, V2, T2. Again, we are going to be taking a simple one, a gas, and we are going to be making sure number of moles is a constant, because something we'll have to maintain as a constant over there when we are doing the calculation. In this scenario here, I am taking a gas in a box and I'm making sure no gas is escaping out or coming inside. Okay. So if this is the process which is going to be happening, it can happen under any condition, any path. I do not really care. Now, how do we proceed for this over here? How do we analyze this and get this sorted out? Thing here is, let's say this is going to be a random path. Alright, so we can say delta S for this random path should be equal to Q reversible for S1 to S2. The random path here is also going to be S1 to S2. But it is not a particularly well-defined path. It can be any kind of a path which you are proceeding with over there. The Q reversible, on the other hand, should be for a reversible path over there. So Q reversible for S1 to S2 divided by T. This is basically how we are going to be proceeding here. Of course, you can integrate and get the thing also done. It doesn't make a difference. Now, in this part over here, how to proceed and analyze how to get things done or sorted out over here. What we are going to be doing is, we are now going to create a new state in the middle, S3, or we can create another new state in the middle, S4. Let's not go for the other new state, we'll go for one of the things here. Let's say I'm creating a new middle state here, S3, in such a way that I'm going to have this path known to me, and this path is also something which I can basically now start predicting. So the idea here is, let us say I'm now having this middle state S3. Okay, what I'm going to be doing is, I want to calculate Q reversible for the random path. Now, if I can calculate Q reversible for the overall path, Q reversible is a state function. So Q reversible is a state function. Now, what is the advantage of having it as a state function? The advantage is this: Q reversible from S1 to S3 plus Q reversible from S3 to S2 should be equal to Q reversible from S1 to S2. This is what path function, this is what a state function basically means. So if Q reversible should work like a state function, or it does work like a state function, automatically we are going to be having this mathematical aspect of it being applicable over there. So what we will now be doing is, we will simply be applying the mathematical aspect here and proceeding on over there. So what is the idea here? S3 is going to be, let's say, S1 to S3 path here. We can take it as some kind of a specific path. Let's say I'm taking it as an isobaric path. If it is an isobaric path, what does it mean? Constant pressure is maintained or constant volume is maintained?
Constant pressure.
Good. So S3, what can I know for it? What all will I know?
It exists in the same pressure as S1.
Good. P1. Now, the next thing here is this. I suppose I should have discussed for the other process once a little bit earlier. I'm not sure if we discussed it last time. Isothermal. Did we discuss isothermal process last week?
I think so, sir. Yes.
Okay. So isothermal process means you're going to be having it at constant temperature. So delta S at constant temperature is very straightforward. So Q reversible, what is the value for constant temperature case over there? nRT ln of T2 by T1. So you're going to be having this as nRT ln of, in this case here it will be V2 by V1, because temperature is being maintained a constant here, and you're going to be having nRT ln of P1 by P2. You're clear with this now? How do you get this over here? Because from first law, delta U should be equal to Q plus work done. Correct?
Yes, sir.
So delta U for isothermal is how much? U is a function of amount of substance, temperature and state of substance. State of substance, whether it is going to be physical state is what I am supposed to be putting over here. Physical state, not just state in that sense. So if I am going to be having the gas not changing from a gas, remains a gas, temperature is a constant, and the number of moles of the gas is not changing, I am going to be having internal energy not changing for the gas. Same way, H is also the same thing. So delta U at a constant temperature is simply going to be 0, which means this is going to be Q plus work done. Meaning we are going to be having delta U at a constant temperature process 0 equal to Q plus work done. If I take a reversible process, it will be Q reversible plus work done reversible isothermal. This is something we know. Work done reversible isothermal, we have calculated it as, you're familiar with this formula, na? nRT ln of V2 by V1. Okay, that looks like you're not particularly familiar with this. Maybe I've discussed it too long ago, or maybe you've not discussed it at all. Work done lavandi, you're going to be having, let's say, a process which is isothermal happening. Then we are going to be having the system going from, say, state S1 to, say, something like state S2. Let's say this is pressure, let's say this is volume. Okay, so what is going to be happening here? You're going to be having some pathway happening in between this. So the game is going to be, work done is going to be the area under the graph. So if it is going to be the area under the graph over here, work done is equal to minus P dV. Correct. So all you have to do is integrate over here. How do you integrate in this particular case here? You're going to be having pressure. It's an ideal gas. So for an ideal gas, you'll have certain straightforward definitions being applicable. We'll have PV is equal to nRT, meaning we are going to be having P being equal to nRT divided by V, meaning my work done in this particular case, if I have to put it down again, so work done is going to be minus P dV. So minus P dV na pressure, now we can substitute over here. So work done works out as equal to minus nRT by V dV. Integrating it, we end up getting work done reversible isothermal working out as minus nRT ln of dV by V. Integral of dV by V is going to be effectively ln V. So ln V means you will end up having it as minus nRT ln of V2 by V1, because it's going to be going from volume V2 to, from volume V1 to volume V2. So this is basically going to be work done in an isothermal manner. But if I am going to be having volume changing over here, instead of putting it in that fashion over there, I can also write volume in terms of pressure and proceed on over there. In the sense, this V2 by V1 here can now be slightly changed over here. So work done reversible isothermal works out as minus nRT ln of V2 by V1, which effectively we can also write it in a slightly different way, in the sense, you're going to be having pressure being equal to nRT by V, meaning V is going to be the same as nRT by P, meaning V2 by V1 can effectively be written as P1 by P2. So it works out as minus nRT ln of P1 by P2. So this is another way into basically putting up the same thing. Let me just check if my integration part, is my integration correct here, dude?
Yes, sir.
Okay, alright. Because I don't remember integration formulas properly. It's been ages since I have had to check that particular thing. I don't bother with it anyway now. So, alright. So, effectively you're going to be having this as the scenario in this particular case here. So, this is going to be work done reversible isothermal. Now, what is the advantage we have from here? Delta U for the isothermal process is 0. Meaning Q reversible plus work done reversible is going to be 0. So if this plus this is 0, that means we can write Q reversible is going to be nothing but minus of work done reversible. So if I am going to be having an isothermal process, then automatically this will be the same as minus of work done reversible isothermal, which of course works out as nRT ln of V2 by V1 or nRT ln of P1 by P2. You're clear with this so far properly?
Yes, sir.
So, of course, if I'm going to be having delta S for an isothermal process, that is supposed to be Q reversible by T. Q reversible, we just got the formula done over here. Q reversible for an isothermal process is going to be nothing but something like this. So, we'll end up having in this particular case here, this can be written as nRT ln of V2 by V1 divided by T, or nRT ln of P1 by P2 divided by T. Either way, I'll have the T and T cancelling, resulting in, very simply put, nR ln of V2 by V1 or nR ln of P1 by P2. This is going to be delta S at constant temperature for any isothermal kind of process. I don't care what path it takes. It can take a reversible, irreversible path, it doesn't matter. This is based on the isothermal path being taken. You're clear with this particular formula now properly, yes?
Yes, sir.
Understood this?
Yes, sir.
Okay, now we go back to the random path. In that random path, what I'm going to be doing is, I'm going to make it in the first path over here as an isobaric path. But the second path here, I am going to try to keep it into an isothermal path. Why? Because I need to not just know one state over here for system S3. For S3, I need to fix two states. I can't just fix one state, because one state is going to be completely hanging, which we cannot describe as what it is going to be. In this case here, what I'll do is, volume will be some V3, complete unknown, I do not care what it is. I am allowing the volume to float as much as it can. But I will make sure temperature is going to be T2 now. So what I am doing is, I am now having an isobaric path. So in this here, from S1 to S3, I am creating an isobaric path, wherein in that isobaric path, I am maintaining pressure a constant, but I am taking temperature from state S1 to state S2's temperature directly. But I am allowing volume to float as it can. Do you understand what state S3 is going to be?
Yes, sir.
So S1 to S3 is going to be a nice isobaric path. S3 to S2 is going to be an isothermal path. Both the paths we can now solve for. So how to proceed over here is, we will now have delta S state S1 to S2 can be written as delta S of state S1 to S3, which is going to be isobaric, plus delta S for state, I suppose I should write it more properly at least, delta S for state S3 to S2, which is going to be isothermal. So this is the general way to proceed and solve for this over here. So let me expand on this in the next part over here, or after this only it is better to expand on it. So if I am going to be having delta S for a random path S1 to S2, we are going to be having it as delta S isobaric S1 to S3 plus delta S isothermal from S3 to S2. So now what is S1 to S3 isobaric here? It is going to be something where the temperature is going to be the same. S1 was P1 V1 T1 to final state is P2 V2 T2. So directly put everything for T2 only, and I mean for state S2 only. Don't care about it beyond a point. So it works out as isobaric. We have just seen the formula a while back. NCP ln of T2 by T1. Plus isothermal, we have just had a look at that particular formula. Isothermal ke liye, these are the two formulas over here. In this case, what is known for S3? S3 is going to be a state where we are going to be having it as P1, T2 and some unknown V3. I do not know this unknown part V3 over here. This V3 is a complete unknown. So when I don't know what is S3's actual volume there, you are not going to be using the volume formula. You will be using the pressure formula here. That is, in this here, we do not know the volume part over here. This part I do not know, or this part for this I do not know. One of them is not known. But we know the pressure ones properly. So use the pressure application of the formula. So in this case, it will end up being plus nR ln of P1 by P2. I should not put it as V2 by V1. In this case, that is not the same. So you're going to be having this as one path over here, or we can actually put another path completely. In the second path there, what we are going to be having is delta S. I'm going to be going from S1 to S2 again, same S1 to S2, P1 V1 T1 to P2 V2 T2. I don't care what path it is taking, anything is allowed there. But this time, instead of breaking it into isobaric and isothermal, I am going to break it into isochoric S1 to S3 plus isothermal S3 to S2. In this case, what will be S3 gonna? Tell me what S3 state should be over here. Prajwal?
Yes, sir.
What should S3 be like over here? It is after an isochoric path. Isochoric path na, what should be a constant? Volume should be a constant.
Yes, sir.
Next path is going to be an isothermal na. In that second path, temperature should have been a constant.
Yes, sir.
So from volume V1, it should have stayed at volume V1. From temperature T1, it should have gone to temperature T2. Because this path is isothermal.
Yes, sir.
Right. But obviously something has to be allowed to float. What will be floating? Pressure. This is going to be at some random pressure P3. We don't know what pressure it is going to be at. We cannot find it out also. It is just not possible. It is going to be at some random pressure P3. So this is going to be my state S3. Are you following here properly?
Yes, sir.
So in this particular case here, if I want to now put down the formula for this over here, how will this work out over here? It works out as state S1 to S3, same isochoric there. So it works out as NCV ln T2 by T1. Plus we are going to be having NR ln of, in this particular case here, it is an isothermal path, but what do I know for it? I don't know the I don't know the pressure, I know the volume. So in this case, I'll be using volume over there, which is going to be V1 as the reference over here. So it will be NR ln V2 by V1. Do you understand what is happening? In that isothermal path, what is the actual thing which is being changed here? In this isothermal path, temperature is maintained the same, but I'll bring the volume from V1 to V2. When I bring the volume from V1 to V2, automatically whatever this P3 was, that will also change into P2 over there. Do you understand the isothermal path here?
Yes, sir.
So you will have, for any random process, two different formulas applicable for delta S. I'll put them down separately here. If it is a random process, state S1 to S2. One is isobaric isothermal path, another is isochoric isothermal path. Both cases you have to be careful how you are applying it. So if you put NCP here, ln of T2 by T1, you have to have it as NR ln of P1 by P2. No escape over there. That is, in the sense, if you put CP here, this has to be P1 by P2. That is a critical thing. CP here, now this has to be P1 by P2. If you put CV and go, that means isochoric path if you are taking NCV ln T2 by T1, then you have to definitely put the volume components only over here, NR ln of V2 by V1. So the idea here is, if you are putting CP, you have to have P1 by P2. If you put CV, you have to have V2 by V1. You are clear with the formulas for deltas for a random process?
Yes, sir.
This is for any random process, any kind of process which is going to be gas in a box. As long as number of moles is not changing, you can proceed and go for it like this. If it is going to be a reaction, it is same as every other time which you have done till now. If you are considering deltas for a reaction, it is simply going to be entropy of products minus entropy of reactants. Products minus reactants. So bluntly, products minus reactants will give you deltas for a reaction where something is changing obviously. And similarly, when you are going to be having deltas for a reaction here, there are going to be, of course, understandings to have, to look at over here. What does this basically mean? Deltas for reaction means the number of energy states in which you could store energy, or the number of accounts into which you could store energy, of the reactants is going to be S of reactants. S of products is the number of energy states in which the products are able to store their energy into. So accounts of products minus accounts of reactants, what is the change in the total number of accounts which have happened during the reaction? That is effectively delta S of a reaction. Other than this, I think we are cleared off with entropy now. We can go for Gibbs energy now. Now, Gibbs energy, what is the reason to define this fellow over here? It is defined as H minus Ts. So let us try to understand what all do we know about the system right now and why are we playing around with this? Why are we doing thermodynamics a little bit? What is the purpose of doing thermodynamics? To understand the different variables involved in a reaction, to figure out what exactly is happening in all of those cases over there, what is the mathematics involved, how are the mathematics connected, and why are we doing all this? At the end of the day, to control and extract work for ourselves, get ourselves into the benefit side now. We are studying all this crap to control it so that we can get that thing to do something for us. That is the game over here. We are not interested in anything else over here. We are looking to get gain out of the system or whatever we are playing with in all of this over here. That is what we are interested in playing with over here in this case here. So how do we go about it over here? Well, we define a new term right now, and just like all human beings, mathematically figure out what should be the maximum you can extract, then extract and see if you can get it. For instance, what is your Narayana system which is being followed there, KK's campus, China system, whatever it's called over there? Basically, they have collected enough data from previous students. They have understood if we do this, efficiency is increasing. If efficiency is increasing, okay, that is going to be worthwhile for us. Now the real game is going to be, what do you define as efficiency? How do you define what your output is supposed to be? So ideally speaking, in your campus over there, the output is based on what is going to be most beneficial for the student, and how do we maximize students' comfort, how do we maximize students' output, and how do we maximize students' rank. That is the game over here. So for that, they have experimented. They have understood that some variables are more meaningful, some are not that meaningful. They keep adjusting slowly here and there to make the system better. Now, but ultimately, they need a comparison scale. How do they compare? With previous year's data and with assumed efficiency. If we assume 100% perfectly, if the student is following everything, what will the student get? Something like that will be an assumed type of thing. In this case here also, for any reaction, any process which happens. Remember, thermodynamics is about understanding anything which happens. So what people were doing around 200 years back was, this was around heat engine time, steam engine time. They wanted to understand, is the engine efficiently delivering me what I want? Is this the maximum efficiency of the particular engine? If I am going to be giving it some fuel, it is going to burn it, it is going to produce some work for me. Is this the best amount of energy I can expect from the engine? That is basically the question which was being thought about at that particular point in time. So what they wanted was something which will basically be a mathematical representation of maximum work this system can do. So let us try to understand the maximum work a system can do. If I am going to be having a system, a gas in a box, okay, this is going to be my system. If I am considering maximum work the system can do, who is basically measuring this? Is it the system measuring it, or is it surroundings measures it?
Surrounding.
So surroundings is what does the measurement. So in a sense, what is happening over here? The surroundings is now trying to extract energy from the system, because work done is technically a form of energy. Correct?
Yes, sir.
So maximum work means it is a form of energy. So what does this actual statement really represent? This represents maximum energy surroundings can try to ever remove from system. Fair enough? Do you understand the English language over here properly?
Yes, sir.
Because only when you understand the English language will the definition start becoming more and more obvious. Okay, now let us now try to understand the system. Actually, over here itself, let me put it. We have discussed different things about the system, correct? So let us talk about what is internal energy of the system. What does U represent?
The internal energy of the system.
Yes.
The internal energy of the system.
What is that?
The energy stored inside every molecule of the system.
Good. So it is going to be the total energy accessible by particles of a system. Correct? That is basically what you said.
Yes, sir.
So this is going to be total energy accessible by the particles of the system. But this is not the total energy of the system, because the system is occupying some space by pushing against the surroundings continuously. So we have a new definition, H. This H is going to be total energy of the system, including the energy the system has invested into occupying the space. So this works out as H is equal to U plus PV. We are of course going to be having nuclear energy and nonsense, but we are not going to consider that. So the total energy of the system overall is going to be H. U is going to be amount of energy which is accessible to the particles of the system, where we are not counting the energy of the system's molecules investing into the space they are occupying. So if this is the case, now let us now try to understand what is going to be the maximum energy surroundings can extract. So if I am considering maximum energy the surroundings can extract, from system, H is the total energy the system is having. So obviously that H has to be involved in the process over here. H is going to be part of it. And the system's matter, or the molecules or the atoms making up the system, cannot be destroyed. All matter is basically not going to be capable of destruction, because if you destroy it, you'll have to go for Einstein's equation. That is going to be a completely different type of game there. So in this case here, we are going to assume that the system's molecules are not going to get destroyed. If they are not going to get destroyed, then the system's molecules have to exist. If they are existing in whatever state they are present in, they will be occupying some number of energy accounts, minimum number of energy accounts they'll have to occupy. The minimum energy which you have to basically, not minimum energy, I would say it as this, the energy which has to be stored in those accounts. Per account, the amount of energy which gets stored is of course decided by temperature. Temperature is the amount of energy stored, or decides the amount of energy. You can say, decides the amount of energy stored by molecules of a particle. By particles in a system. In each account. Account of course can be looked at as a degree of freedom, or you can think of it as one way of movement, or any kind of account where energy is basically going to be stored. So effectively we end up having the maximum energy which we can extract is going to be, simply put, the total energy available minus temperature into the number of energy states, or the accounts, number of different accounts which are applicable at that particular given condition, which is basically what we are now defining as G. So G was originally defined from one perspective, to find out how efficiently a machine is running. Let's say some industrialist has made some random huge machine. Okay, some power plant is basically producing energy. He wants to basically, he's making good amount of money every month, but he's got a bunch of employees. He has to make sure he's shouting at his employees regularly. and telling them, see, you are not doing work properly. That is why I'm not making more money. You are doing wrong. How do they work in Chaitanya or Narayana or your campus over there? They try to poke every time for no reason. Even if there is no reason, even if things are going perfect, the boss has to come and say something and find some fault to improve on. Some way to basically increase efficiency, some way to basically keep pushing ahead. What will they do? They will come up with a theoretical analysis over there. Okay, this is the process which we are actually doing. In this particular process which we are actually doing over here, this is the maximum energy we as surroundings should be able to extract out. If we cannot extract it out, that is a mistake, that is a problem. So we need to understand what is our efficiency at. So for that they defined this. What was G? G was basically maximum energy surroundings can extract from system, or you also call it as maximum possible work done. We get very close to this if we are going to be doing the process via electricity. Alright, people kept moving towards the highest efficiency possible, and eventually they did reach it also. They did come very, very close to it. You can say we did our calculations of delta G based on electrochemistry predominantly. So Gibbs free energy is defined as H minus Ts. It is the maximum possible work which you can extract out of a system, or maximum possible work done by a system. Now this of course changed a lot as things went across. When you're going to be looking at delta G for a reaction, we can effectively write it as delta H minus delta of T into S. So we end up having, if we are maintaining a reaction at a constant temperature condition, we'll end up having it as delta H minus T delta S. Basically speaking, what is T into delta S, or what is delta of Ts? Delta of Ts means S was defined as what? S is defined as Q reversible by T. So we'll end up having delta of Ts actually being delta of Q reversible. So from that perspective, we'll actually end up having in this particular case here, delta H is equal to, delta H minus T delta S. Why can we write it like this? Because simply speaking, Q reversible is going to be something which has many different formulas. We have just seen the different ways of representing Q reversible. What are the ways of representing it? Q reversible, we have just seen it. I don't want to put down it again. That's too frustrating. I'll just show you that page again. Yes. So Q reversible for isobaric, isothermal, and for a random process. This is for the isothermal process. And next one for isobaric would have been in the previous page here. Where's isobaric crap? This is here. So isobaric and isothermal are basically over here. So you're going to be having isobaric pathway, you're going to be having this as the Q reversible associated with it. So Qp in this particular case is going to be nothing but NCP dt, which works out as whatever you're going to be having as Qp there. NCV dt is going to be the case for Qv over here. And effectively speaking, for the, what was this one here? Q reversible for isothermal. For an isothermal process, this is going to be the scenario here. So for each of the different types of processes, we have had a look at it. For a random process also, we have had a look at it over here. Now, if you are going to be having it being a gas in a box, you can use any of those formulas. You can substitute Q reversible over there and proceed. If it is not a gas in a box, it is going to be a reaction, then this works out to be a much more meaningful and useful thing to look at. We end up having delta G of a reaction being equal to delta H of a reaction minus T delta S of a particular reaction. And there are certain advantages to this thing over here. One major advantage which starts coming out is this. Later on, as scientists started learning more and more about what this maximum work extractable is going to be. Initially, scientists effectively looked at it simply as maximum energy surroundings can extract from the system. But that started changing slowly into something like this. The concept started evolving. Now we can look at the evolution from a theoretical perspective or from a mathematical perspective. Math perspective, say, I'll discuss the cases separately. Theoretical perspective, let me just put it like this. So we are all familiar with what to say, the reality that when something happens, it is being allowed to happen. Not everything happens naturally, or if something happens unnaturally, there are reasons for it. So when you're going to be having a process happening, this basically started teaching, or rather, scientists did not know this was going to give them this. But this effectively led to understanding why a reaction actually ends up happening. Scientists found a universal condition which you can think of as an actual universal condition. If a process must happens, not must happen, if a process happens, it is being automatically favored by the universe. If the universe does not want it to happen, that process will not happen. So what happens is, if a process happens, automatically you can think of it as it pays a tax. In a sense, the theoretical understanding goes like this: it pays a tax to the universe. In the sense, the universe is what is allowing it to happen. If the universe doesn't want it to happen, that process won't happen. So it has to give something back to the universe. What is the universe over here? If any process is happening, we can consider the universe to be nothing but system plus surroundings. So in a sense, if the universe has to allow the process into happening, then effectively speaking, it needs to fit certain rules of the universe over here. What is the mathematical rule of the universe from this perspective here? Scientists found that process happens only when delta G for the process is going to be negative. If delta G is not negative for a process, that process won't happen. For instance, let us consider India as a country. There are some weird examples which we can take over here which will help you understand this better. If I'm going to be considering India as a country, we were colonialized by the Britishers, correct? We suffered for a huge amount of time. Yes or no? That process happened. Why do you think that happened? We allowed it to happen to our own country, na? Why did we allow it to happen? What could be the
Because
reasons?
we did not have much energy.
No, we were the richest at that time in the world, around 20 to 25% of GDP. Energy we did not have. In a sense, that is not a wrong way of looking at it. But energy is not what I am considering here. Now I am considering why that happened. Why do you think we have let it happen? Why do you think it happened at the end of the day?
So unity wasn't there.
Correct. Unity wasn't there. Why was unity not there? If unity is not there, did we have higher entropy or lower entropy?
Lower entropy.
We had higher
Higher
entropy.
entropies. Higher
Okay.
entropy.
We
Yes.
had higher entropy. So what happened was, when the situation was in such a way that we did not have much, what to say, unity really internally, basically that was a stage of very high entropy for us. So if in that high entropy stage we ended up being in a scenario where what to say, temperature was made very difficult for us. So think of it like this: delta G technically is delta H minus T delta S. Correct. So from that higher entropy stage where we were more fighting internally, we preferred to go back to a stage where we were more united. Why? Because we thought that would give us more stability in the process. So what did we really not have in the beginning? When the Britishers came in, we did not have enough stability. We had a lot of internal nonsense. We did not have enough stability. So for the sake of greater stability, what did we as a people do? We let our freedom get sacrificed. That is what happened, correct?
Yes.
Britishers brought in more better technology, newer things, which basically technically made our lives easier. more addictions, more what to say, railroads, more faster movement. All of that was brought in. They were all things which definitely increased trade and controlled the population in a more efficient manner. So effectively, it increased stability for the country. So when the British came in, stability is what we valued over there. So in that process there, delta G became negative. How? Because the stability gained, we can say, was greater than the cost of loss of freedom. For example, let us say I am going to be having water in the form of liquid water. If I throw it into a fridge, what is happening to it? Into a freezer. It basically freezes into ice.
Yes.
Correct? So let us now consider that process. Water liquid is going to become water solid. If I consider this process, this is a process where freedom has been lost in the process.
Yes, sir.
So this is similar to the, what to say, process where our freedom was taken away as well. In a sense, freedom was lost in our, what to say, when the Britishers conquered us as well. So what is basically happening over here? This water liquid becomes water solid, but it doesn't happen at normal room temperature. It happens below 0 degrees Celsius, correct?
Yes, sir.
So what is exactly happening in this water liquid becoming water solid process over here? In this process here, you are going to be having the molecules gain extra stability, correct? Because in water solid there, you are going to be having ice molecules or water molecules in a very beautiful pattern where they are internally hydrogen bonded and connected with everything, forming nice beautiful patterns in the entire structure there. You are familiar with the structure of ice, how it looks, the hexagonal patterns there?
Yes, sir.
So the molecules effectively gain much more greater stability in the process. So we can effectively say molecules have gained stability now. What is the delta H for this process? Is it negative or positive? What is it? Is it positive? Is it negative? Liquid is becoming solid. Think of solid becoming liquid. If I have ice in my hand, if it melts, does my hand feel cold or does my hand feel warm?
Once again, sir, there was an internet issue. Can you repeat?
Okay, internet issue. Okay, So I am interested in water liquid to water solid. What is the enthalpy change in the process?
Negative, sir.
Negative. Good. Why is it negative? Can you quickly explain?
So because water in solid state, that is in ice, it is more stable, so it would lose some energy.
Good. All right. So enthalpy change of the process is going to be negative in this particular case here. So this is basically the idea over here. So delta H is negative. But in this process, I am going to be also having delta S of the process. That is also negative in this particular case here. Correct? Because you are going to be having the molecules are now more rigidly packed and they cannot move so much. They can vibrate, rotate, all of that, but they cannot really move out of their location anymore. So they have lost some freedom in the process. So you're going to be having loss of freedom is basically going to be the reason for this. So in this process of water liquid becoming water solid, you are going to be having delta H for the process is negative, delta S for the process is also negative, which is pretty much the same as what happened in our Indian history. Why did we let the Britishers conquer us? Because we were already a conquered people. We were broken. We were already a broken set of people who were broken because we were already conquered by a foreign power called Mughals. And because Mughals had conquered us and kept us conquered for so long, when we got frustrated with the Mughals, when our people basically did not have good standard of living, you can think of it as temperature basically kept decreasing. Our amount of income which we could put in every individual's hand was decreasing. As that happened, what happened? We allowed a random outsider to again come and conquer us, and this outsider did not leave for another 250 years basically. So we thought the Britishers would be a better evil compared to the Mughals. Both were evil, or that both did what they had to do. I would not say evil. The Britishers also did a good amount of help for us. Our railroad system, our trading, everything has basically improved because of them. They have given us all of the sciences which they basically collected. All of that they did. They also pillaged and completely left us extremely dirt poor in the process. Okay, so the idea here is, let us now look at the same reaction now. H2O liquid is becoming H2O solid. What is happening here? Delta H for this process over here is going to be negative. Delta S for this reaction is also negative. And the reaction happens below 0 degrees Celsius. This is what we have to start understanding now as to what is exactly happening. So what is really happening over here when I now consider it from the delta G perspective? Delta G for the reaction is delta H minus T delta S. Now, mathematically speaking, scientists had experimented out and found that if delta G is negative, only then reaction is allowed into happening. So let us try to understand in this case. This is a reaction which happens. We know delta H and delta S signs over here. We know theoretically it happens below 0 degrees Celsius. Let's try to understand what could this mean mathematically over here. From a mathematical perspective, I am writing delta G here. This is going to be delta H minus T delta S. So, if I want delta G to be negative, what does that condition translate into? That condition translates into comparing delta H minus T delta S to 0 basically. So, if I compare that with 0, we end up having delta H minus T delta S here if it has to be less than 0. What does that translate to? That translates to delta H should be less than T delta S. Or we can say temperature should be, in this particular case, should be negative, na? Negative means not less than, it should be more than basically. Oh, but we are having anyway negative values only. Okay, alright. So effectively in this particular case here, we are going to be having delta H and delta S being negative values. This is going to be a negative value over here. This is also going to be a negative value. I want the net to be less than 0. If I want the net to be less than 0, what does that really indicate over here? If I am applying modulus in this particular case here, if I need the net to be more than 0, less than 0, I want the delta H which is negative to beat this minus T delta S, because minus T delta S part over here ends up becoming positive. So this is a negative sign here, another negative, it becomes a positive. So effectively speaking, if I want this to be less than 0, the mathematical condition here will work out as something like this, where we are going to be having, if I am interested in the net to be negative, that means the modulus of the delta H should be greater than the modulus of my T delta S. If it can beat this, then yes, we can say it will be more negative. Overall, it will be less than 0. What does this effectively translate over here? This translates to temperature should be less than mod of delta H by delta S. This is basically what we are going to be.
Are we measuring temperature in Kelvin?
Yeah, of course, yeah, all of these cases, temperature is in Kelvin. Da. In this particular case, 0 degrees Celsius works out as 273 Kelvin.
Yes.
We are always going to have temperature only in Kelvin, never in degrees Celsius. Degree Celsius is just the value we remember, that's all. So, in this particular case here, mathematically speaking, if I am going to be deriving this out, delta G is negative. What that translates to is that for delta G to be negative or for delta G to be less than 0, in the current case where I am having delta H is negative and delta S is also negative. For this particular case here, if I want delta G to be less than 0, what does that really mean? It translates into temperature being less than modulus of delta H by delta S. This delta H by delta S is going to be some particular value or some number. So this is going to be some number effectively. So effectively we can say temperature should be less than a particular temperature or particular number or you can think of it as particular temperature, which we are actually getting over here, which we call as temperature of fusion, or in this case melting point. So if I am going to be considering the process of water liquid becoming water solid, what do we get from the analysis over here? We end up getting that if delta G should be less than 0, that effectively translates into a condition wherein it tells us that I should be having temperature being below a particular given value for this reaction to happen. What is that given value? Below melting point or below freezing point. So melting point, in this case another name for it is freezing point. So below melting point or below freezing point is what we are getting over here as the analysis out. So this is basically a perfectly acceptable condition, which is perfectly synchronizing the mathematics over here with what is actually happening in reality as well, with the numbers which we are getting in reality. So we are going to be having each case like this. We will have to study all possible scenarios, because ultimately what are we really doing over here? We are just analyzing what our experiments are basically giving us in reality. We are trying to connect it with a mathematical function to see if this mathematical function is useful to us in some other way. This mathematical function delta G was originally discovered or originally made to find out what is the maximum work you can extract out of a system. From there, they realized, oh my god, this is a much more powerful tool which helps us understand why a reaction really happens. And how do I make sure I can now get into newer conditions for a reaction to happen. So for instance, now let us take another type of process. From here, we will do the mathematics of it and then I'll describe the example. If I have, say, delta H for a reaction being positive and delta S for the reaction is also positive. Can you give me an example of this kind of a process? Boiling of water, correct? This will basically, or what to say, fusion of water, both will basically come into this over here. So let's say I'm going to be having H2O liquid becoming H2O gas. In this, liquid molecules are becoming gas molecules, so their freedom is definitely going to be increasing, meaning we can say delta S for this process. Let's call it as reaction 1. I'm getting irritated by writing whatever every time. So delta S for 1 is going to be positive. Simultaneously, delta H for this first reaction is also positive. Why? Because liquid molecules are going to be having lesser energy compared to gas molecules. Gas molecules are going to be having much greater energy and they are less stable in the process over there. So delta H for this is going to be positive. Delta S is positive. Now let us look at the mathematical condition and try to understand this over here. So in this particular case here, let us, before going to the mathematics, let us try to understand theoretically first. In this case here, the idea here is a reaction will happen if the molecules in the process are gaining something overall. That is, for a reaction to happen, system should feel like it has won. If the system does not feel like it has won, the reaction will not happen. So in this case here, what is happening to the system's molecules? System gains freedom, loses stability. Why has it lost stability? Because it has gained energy in the process. Correct? This is why it has lost stability. Fair? Yes or no?
Yes, sir.
Okay. So in this case here, for the system to show a net gain, for system to have net gain, what does it really mean? It means the gain in freedom should be worth the loss of stability which has happened over here. In the sense, if you want to go play or enjoy this particular week where you are having holidays, you should make sure that the amount of freedom you are able to enjoy is more than worth the amount of stability which you will be losing in the process. Because if you are going to be enjoying this week completely and enjoying your freedom totally, one way to do it is not have any classes and not practice anything. Actually mentally go chill, waste some time. Correct? but it should be worth the amount which you are going to be gaining in terms of freedom. If it is worth the amount, then you will do it logically, right? So in this particular case, we'll talk about the other case also in a while, because reality goes in the other direction only most of the time. For a system to have net gain, the loss in stability must be compensated by the gain in freedom. Correct? That is the logic over here. So if you had a girlfriend at this time and your parents had allowed you both to travel around as you wished at this time, then you will happily throw away your notebooks and your classes to enjoy a proper freedom at that particular period of time. Fair? Or if you had like proper meaningful ways of wasting time in a proper sensible manner. Right now, you don't have that many avenues. That is one of the advantages of going to a village. You are not going to have all access to your everything, so to say. I think everything should be available now, na? Most of your internet is available, means everything is available. Internet has become that way now. Addictions are available everywhere. Fair enough. So it is a choice only which you have to keep making. So the idea here is this kind of a process will happen if the gain in freedom is more than the loss of stability in the process. So let's try to understand what that translates to in theory first. Then we will see if the mathematics also agrees with that. So gain in freedom is going to be T delta S. This should be greater than the loss in stability, which is going to be my delta H aspect here. So technically it says temperature should be greater than some value of delta H by delta S. In this case, modulus is also necessary, of course, ideally, but you don't really require it over here because both are positive in this scenario here. So this is what we are arriving at over here, which agrees with our theoretical, experimental data. That is, this process happens above boiling point. Correct. So this happens above boiling point. So if it happens above a particular temperature, that is basically what we are getting as the logical understanding from system should have some access to some net gain. Now let us try to see the delta G part of things over here. How does this track out from delta G perspective? Delta G is going to be delta H minus T delta S. So delta G should be less than 0. That is the idea here, which means delta H minus T delta S should be less than 0, which means in this particular case we are going to be having delta H being positive, delta S is also positive. So we should effectively have the T delta S part effectively overcoming my delta H part in this case. If it can overcome the delta H part here, I will be having delta H minus T delta S being negative over there, which means temperature should be greater than a delta H by delta S, which is again the same mathematical condition which we arrived at, which agreed with our experimental data also perfectly. So in this case also, this condition which was made up randomly to explain if a process can happen is perfectly fitting into it. Delta G being negative, delta G of a process being less than 0 is perfectly agreeable in this particular case also. Now, so you have seen two of these cases. Let's say one more case now. So in the next case here, what we are going to be looking at is delta H is negative and delta S is also positive over here, meaning delta H is negative now, stability is gained. And freedom is also gained. So let me ask you a question here. Why do your parents and why do you like to go to your village when you are having a decent set of holidays? Think logically and give me the blunt answer. You feel it is more productive? In a sense, you are having good amount of time to study, you have good peace of mind to study. In fact, you willingly wanted extra classes during this week of Pongal. You are more than happy for that. Now, so it is more productive, it feels better. Why does it feel better? Because your stability is also increasing in the process. And your freedom is also increasing naturally. Why is stability increasing? Because you are able to find more motivation to do things which you have not done. It is much more peaceful and much more comfortable to do those things. Because other option is going outside and getting to talk to relatives who will ask unnecessary questions whom you will have to give answers to. Not particularly convenient, not particularly comfortable. So better option, sit and study at home. Very nice beautiful apartment or beautiful village house will be available, which is like perfect for studying. Nice and quiet, nice and silent, no irritation. All facilities are anyway available, internet is available, everything is available. So stability you can increase comfortably, but at the same time you are also feeling freedom increasing, because you are not in the same place you are normally present at. You are in a new place, you can roam around if you want. Yeah, you have access to internet also. Your freedom also feels greater. You are 500 kilometers from your classes. Which village have you gone to?
Around Vijayawada, sir.
Around Vijayawada. So proper far off then. 200, 220 kilometers, huh? Or
Yes,
300?
sir, around 250.
250, okay. Huh? So effectively freedom has also increased because you are very far away from your campus. You are very far away from anything around which you have been used to for the past, like say 5-6 months. So technically freedom has also increased, stability is also increasing over here. So you are more than happy to travel to your village and chill out over there and have your own extra bit of freedom and extra time without any distractions or lesser distractions to focus on what you want to focus on. If that is going to be to enjoy your freedom more, go ahead. If that is to increase your stability, that is also perfectly fine here. So this kind of a trip to the village, you would never have really resisted against it. You would have been more than happy to go for it. Before your parents suggested it, you might have been more interested in this. Is that a fair assessment?
Yes, sir.
So that happened mainly because in that process, stability is also increasing, freedom is also increasing for you. You are able to feel the increase in freedom, and of course you are able to feel the increase in stability because you got more time to catch up with your backlog over there. So this kind of a process is a win-win-win process. You are never going to have a problem with this. So effectively, if a process is going to be having stability is also increasing, freedom is also increasing, always happens when given chance. So you can think that this process is going to be spontaneous always. So again, I am now defining a new term over here called spontaneity. Delta G is less than 0 na, we call that process as spontaneous process. Spontaneous process na, that process happens or can happen by itself. It doesn't need any external impetus to happen. It will happen by itself, no problem. So that is called as a spontaneous process. If I am going to be having delta H being less than 0 and delta S being greater than 0, delta H is negative and delta S is positive, this is going to be spontaneous always. So mathematically, let's try to understand, is it matching up with delta G being negative over here? If that mathematics is going to match up over here, delta G is going to be effectively delta H minus T delta S. This is negative here, this is positive here, meaning this entire term also becomes negative now. So negative plus negative, this is of course going to be fully negative only, no problem at all. So this is again going to be perfectly agreeing with this kind of process naturally. Now let us look at the last one over here. If I am going to be having delta H being positive and delta S is going to be negative, what is this kind of a process? In this here, stability is lost. And freedom is also lost. By the system. What is the idea over here? This kind of a process is basically something which is going to be never accepted. Let's take a simple example based on something which we can understand easily. Because ultimately energy is something which is most easily understood from the point of view of money. Money is going to be the best form of energy which money is the best way to quantize energy, which we human beings have understood. So let's say you're basically a student who's got pocket money as like say 100 rupees every week normally. Okay, you got 100 rupees per week as your standard condition, standard pocket money normally. Your parents are giving you now a choice. In this 100 rupees per week, you will have to account for any major purchases which you are making. If you're going to collect your money for some time, like say you are going to keep collecting it, 100 rupees is too goddamn low actually. Make it 1000 bucks per week because current scenario inflation. So make it 1000 rupees per week. If 1000 rupees per week is your pocket money, all right, you are allowed to collect that money. But if you are making a large purchase of more than 1000 rupees for one item, you are going to inform your parents. You have to inform your parents. Some amount of freedom is there. If it is less than 100 rupees, you can spend as you wish. If it's more than 100 rupees, sometime or the other you have to inform your parents. If it is more than 1000 rupees, you'll have to inform your parents well beforehand, get their permission and then do it. Okay, that is basically the scenario in this case here. Let's call this what your current life is following. Now your parents are giving you another option here. They're going to give you 10,000 rupees per week now and full freedom. You can spend whatever you want, how much ever you want, whenever you want, whatever you want. You don't need to inform them about anything. Is this case more preferred or less preferred? Would you go for that automatically or would you not go for it?
I would go for it.
You would go for it because you're getting more money and you're getting full freedom. You don't need to account for anything. No problem at all. You'll happily take it up. If let us say they are going to be offering say 800 rupees per week, but they are giving you full freedom. You don't need to inform them of anything anymore. This is something which you will think about. Not necessarily it's the best deal, not necessarily the worst deal. You might have to think about it. Same thing will be the case if you are being offered something like say 1200 rupees per week and similar freedom, more rules. Maybe less than 1000 rupees, maybe above 1000 rupees. Earlier you had to basically account and get permission from your parents. In this case, above 800 itself, you'll have to get permission from your parents, or above 500, you have to get permission from your parents for sure. Something like that. Similar freedom, lesser slightly. Obviously, again, you'll have to think. Depending on what habits you have, then you'll have to decide on what you're going to be looking at. For instance, in this case here, if you are going to be someone who is going to be some kind of a rowdy in the class, who basically has gotten into some good habits, like say alcohol, then you would prefer this option over here, 800 rupees per week but full freedom. Parents cannot ask you anything, nobody gets any control, no problem at all. If you are saving up for something like an iPad, which is going to be very useful, or a Mac, which you know your parents will anyway appreciate if you're saving it up and buying, then this option looks better. Because yes, there is lesser freedom, but it is not like you are going to ever buy something which is going to be too expensive. And if you're going to buy something more expensive, you are anyway going to ask them anyway. So it doesn't matter. This is more preferred. So these two cases over here depend on your habits and what you are interested in for yourself. If you are interested in having a cigarette at some point of time without your parents knowing at all, or having a drink, then this becomes very appreciative and I would say very nice looking. If you are interested in buying yourself a good Mac Mini, or say a MacBook or a MacBook Pro or something of that sort, and you know for a fact you will get permission, then this becomes more efficient. So ultimately it is going to be a choice based on the scenario, but both of these are possible options which you might consider depending on your habits and your requirements. Let's take another scenario where you are going to be getting 400 per week now. And
freedom.
Yeah, worst possible case, no freedom at all. Every bit of money you have to inform them beforehand, account for it. If you are randomly not having some money, your money is checked every day. If you are not having the correct amount of cash which you are supposed to have, you get a whacking. Obviously you will not take this at all. This is a never going to be preferred case, but you will take this under one condition. Under what condition? There is no other option. Correct? If it is forced onto your parents, in a sense, if both your parents are losing their jobs and some bad thing has happened, some accident has happened, so money is tight, you need to take care of them as well now, and what to say, they want to feel a bit like your parents as well still. So obviously in that case, this is going to be your option which you will have no way to not take it up. That will be your only way to take it up. So this path is going to be something which will happen only when it is forced onto you. What does forced onto you mean? It means in some way or another, it is something which you do not ever want to happen. So let us now consider that kind of a thing first and then see when that is going to be happening. So if I have delta G, delta H minus T delta S, of course, what is this path over here which I mentioned? This is the path which is going to be having delta S is also going to be negative and delta H is also going to be positive. Stability is lost, freedom is also lost, both are lost. So if delta H is going to be positive and delta S is negative, in this case, delta G is going to be greater than 0. Always. Meaning delta G for system is always greater than 0, implies this process is not spontaneous, non-spontaneous, does not happen spontaneously.
Sir, what if we like reduce the temperature?
Doesn't matter. Even if I reduce temperature, what is it going to mean? I'm going to have delta H being positive here, minus of minus, what will this be? Minus of minus will become plus, that will still be plus. So I am going to be having temperature lower also, doesn't really help much. Temperature lower, what does it do? It makes you get adjusted more sensibly. What does temperature lowered mean? Temperature lower simply means you're going to be adjusting with this 400 rupees per week and making it feel like the same 1000 rupees mentally. In the sense, you enjoy the same amount of freedom as you did in this and this. You try to do that. But is that going to be real? No. It just means you're basically cutting down all your expenses. Right?
Yes.
And you're going to purposely live like you're happy when you're poor. So that is a mentality, that's a mindset. That is not what is exactly something which is exactly happening. Your freedom has not increased. Your freedom has decreased. So it is not a path which you will choose naturally. But if life forces that path on you, you will choose it. And you will choose it happily to make the best of that path. That is how life is working. Correct? That is what life is about. So what are you doing now? You are basically having lesser freedom and lesser stability because you chose going into IIT JEE path. You are having both lesser right now. Your parents are having both lesser right now. Parents are forced into staying in the same city, making sure they are being available morning and night whenever necessary for you at very specific times. They also have to pay a good amount of fee. All of this is decreasing their stability, decreasing their freedom. But they are doing this. Why? Because circumstances have forced that situation to happen. What does circumstances forcing it mean? It means effectively this. This is a process where delta G is greater than 0. It is non-spontaneous, does not happen. But the universe is very beautiful. How it works is like this. The idea is this. Let's say I'm having a small system here. Okay. If this small system is going to be having delta G being positive, then it will not happen. But if I can now make up a bigger system around this, a nice bigger system around it, if for this bigger system net delta G is negative, then this net delta G negative is what the universe or surroundings looks for. So from surroundings point of view, it is not interested in the tiny delta G which is positive inside. So we can perform a delta G positive reaction. How? By combining it. If we combine the delta G positive of a smaller system, this smaller system is system 1, this bigger system is system 2, which we are having. If net system 2's delta G is negative, then system 1's delta G, even if it is positive, it will be forced into happening. Do you understand what I'm explaining over here?
Yes, sir.
So why do we choose the case where delta G positive is going to be happening? Because outside forced us into it. and then gives us an option if you extend it to this much time or if you extend it to this much amount of people of society. Even if bulk of the country is forced into this kind of a horrible competitive coaching industry, very difficult jail time for kids. What is the advantage? The country as a whole is improving faster and faster and faster because the country as a whole is getting more better students, more better slaves trained into society. Better people, more stronger people who can do more work, who can do more for the country. So that is a beneficial thing for the country. So the country is allowing it to happen. Do you understand the principle over here? Same thing happens everywhere. The light which is basically glowing in your house, in my house over here, all of that is delta G positive. How is the delta G positive happening? It is not spontaneous, na? How is it happening? Because delta G negative in some far off place called a thermal power plant had a huge amount of coal combustion happening there. That was producing a huge amount of negative delta G. That negative delta G was collected and sent through wires to us in our houses, which allows our delta G positive to happen. Do you understand how we have used thermodynamics to control our life?
Yes, sir.
Basically, we first understood this delta G negative is the maximum energy we can extract. What does this delta G negative mean? It means a process for it to happen, it needs to basically absolutely have delta G as negative for that process. What does that mean? It means the system has to gain something in the process for it to happen. We will continue on with this discussion actually tomorrow. We have already gone, or I think your normal bedtime is 10:30 is what you said, na?
Yes, sir.
You're okay with me closing it over here, or you're okay with me continuing on? What is your situation like?
Anything is fine, sir.
Okay, all right. So effectively, you're going to be having in this case over here, if a delta G positive process is to happen, then another net larger system which includes the smaller system should now be considered, and in that larger system delta G should be negative. For instance, the electricity thing, and inside our body, what is happening inside our body? Our human body is also one of the best machines possible. Not just human body, all living creatures are basically the best machines possible. How do the living creatures do the same thing which we are doing outside? Outside our body, how do we do it? We use electricity. What is electricity? Electricity is all about understanding that delta G negative in one place can be collected, sent through wires, and then made to do a delta G positive reaction in some other place. How does the human body do? Same thing. We do something called as ATP hydrolysis.
Sir, once again, what is the delta G process that is exactly happening in, like, say, example, lights?
Think. Does the light naturally prefer to be on?
No.
No. Its preferred state is nothing. Correct?
Yes.
So,
Yes.
the process of the light turning on and showing light out is something where it is basically
Heating
having
of tungsten is positive delta G. Okay.
that delta G positive is going to be for any light. We don't have that bulb anymore. I was about to explain for the LED over here, or LCD, or whatever we are going to be having, but principle is the same. You're going to be having heat energy increasing for that location, and because heat energy is increasing, you're going to be having delta H being positive, and at the same time delta S is also going to be not particularly meaningful because it is not changing physical state. It is in the same goddamn physical state, but it is locked in over there. Correct? So you're going to be having delta S being approximately 0 as well. So delta S is going to be approximately 0, delta H is going to be positive over there, delta G is positive for the reaction. So if delta G is positive for the reaction, how is that going to be happening? Because electricity is being supplied. What is electricity? Electricity is stored negative delta G. That is the ultimate idea of what electricity is going to be. That is, when you are going to be having a thermal power plant where, say, coal is basically being burnt. What is happening over there? Coal is being burnt in that thermal power plant, and we are of course going to be having delta H being negative there, and delta S is also positive there. Why? Because coal is being burnt, delta H is negative, energy is being released in the process, and coal is becoming carbon dioxide. So of course you are going to be having what is a pure substance becoming a compound over there, and it is becoming a gas as well. So delta S is also going to be positive for the reaction. So you're going to be having delta H negative, delta S positive, delta G is highly negative for it. So the highly negative delta G is then stored in the form of electricity, not really stored, it is transported in the form of electricity and then given to us, supplied to us effectively, which allows our delta G positive reaction to happen. The human body also works on a similar thing, excepting in the human body, instead of electricity, we have ATP hydrolysis being the one. ATP hydrolysis is going to be adenosine triphosphate hydrolysis. It is going to be something which has very high negative delta G. Okay, so if in the body there is going to be some process inside my cell which is going to be requiring delta G, which is delta G positive. If I want that reaction to happen inside my cell, how does the body encode it? That delta G positive reaction is combined with ATP hydrolysis. So what do I mean by that? I literally mean that when inside my cell, if there is some delta G positive reaction which has to happen, how will the cell do it? It will then send a few molecules of ATP, as many as necessary, and make them undergo hydrolysis at that spot where the delta G positive reaction is supposed to happen. And if enough ATP hydrolysis happens, that delta G positive reaction can be forced into happening. That is literally how the body does it. Not body, when I say body, I don't mean human body, every living creature. Every living creature does their own form of hydrolysis. Human body uses ATP hydrolysis, or some parts of the human body, most parts of the human body use ATP hydrolysis. Most parts of other living mammals also use ATP hydrolysis. Depending on the type of living creature it is, it might have another mechanism also associated with it. I do not know all the mechanisms there. One of the main ones is ATP hydrolysis. So this is basically how a delta G positive process can be forced into happening. Okay. Now, lastly, delta G over here, how does it actually relate to overall? I did say it is going to be something which you can consider as a tax to the universe, correct? So, that is going to be the last thing over here. Effectively speaking, delta G for a system, if I am going to be writing it, I can write as delta H of system minus T delta S of system. Now, if I am going to be considering delta H for the system, this delta H for the system is going to be nothing but Q reversible for the surroundings, correct? Think.
Yes.
If I am having system, a process happens. System ke liye we can say process can be reversible or irreversible. Everything is allowed. What does irreversible mean? Irreversible means one of the state parameters defining system changes suddenly, correct? So usually what is this state parameter which changes suddenly? This is going to be pressure, usually. How is it pressure? It is going to be pressure external which changes suddenly. So if pressure external changes suddenly, then this pressure external change will now basically allow whatever internal parameters to change as needed. Okay, so this is going to be the irreversible process. But if I am going to be considering surroundings, surroundings is infinite. Nothing can change for surrounding abruptly. Nothing changes abruptly for it, because it is infinity. So if nothing changes abruptly for surroundings, what does that mean? For surroundings, all processes of system, of any system, I don't care what system it is, they are all going to be only reversible. All processes, regardless of what type of process it is going to be, all processes, are only going to be reversible, are only going to be reversible. Everything is reversible for surroundings, regardless of what you consider as process for system, because none of the parameters for a surrounding can ever be changed abruptly, simply because it is infinity. So we can effectively say that the delta H of system is basically going to be nothing but heat released by the system. If it is heat released by system, it is nothing but heat which has been released reversibly to the surroundings. Of course, with a negative sign. Why with a negative sign? Because surroundings is going to be gaining the heat if system is losing the heat. Right? Think. If I am considering delta H from system perspective, if this is negative, that means system has released heat. Correct? This is going to be gained by surroundings. Heat gained by surroundings. So effectively we can say delta H of system is nothing but minus of Q reversible of surroundings. Meaning I can write Q reversible of surroundings to be equal to nothing but minus of delta H of system. Now, same way, temperature, there is no real temperature which we can define for a surrounding because it's infinity. So, what do we mean by temperature of surroundings? We mean the boundary where the system and surroundings are in contact. That is going to be what we consider as temperature from surroundings point of view. So, if I am going to be looking at, well, delta S for surroundings, that can be effectively written as Q reversible of surroundings by temperature at boundary condition. Which means we can now say temperature into delta S. Temperature at boundary is nothing but temperature of system. So temperature of system into delta S of surrounding can be also written as Q reversible of surrounding. Correct?
Yes.
Mathematically this makes sense, which means we can say finally delta H of system minus of delta H of system was Q reversible of surroundings. This Q reversible of surrounding can be written as temperature of system into delta S of surroundings. Meaning I can now say delta H of the system is going to be nothing but minus of temperature of system multiplied by delta S of surroundings. Now, if I am going to be now looking at what is delta G of system. Delta G of system works out as delta H of system minus T delta S of system. Temperature of course is temperature of system. So, I don't need to mention it every time as temperature of system. So, substituting over here, I am substituting this over here completely in this case. If I substitute this, I get it as minus temperature into delta S of surroundings minus temperature into delta S of system. This means I can write as minus temperature into delta S surroundings plus delta S of system. So, what do I finally end up getting mathematically speaking? We get it as delta G of system is equal to minus of temperature of system into delta S of universe, where delta S of universe can be written as delta S of system plus delta S of surroundings. Meaning, what does my actual condition come out as? If delta G of system is going to be in a spontaneous process, what does this mean? This means this has to be negative. If it has to be negative, what does that tell us? Temperature of system is always positive because in Kelvin scale it is an absolute temperature. So if this has to be negative, this basically implies delta S of universe for any process which is spontaneous has to be greater than 0. Do you understand what this means now?
Yes, sir.
So delta S of universe for any process which happens naturally should be greater than 0. Ultimately, anything which happens because something else also forced it into happening, but net system will always have delta G as negative. So the idea here is, what is this really telling us? This tells us that if anything happens in this universe, it should automatically make sure that it is in some way or another increasing the freedom associated with the universe. What is the freedom associated with the universe? In some way or another, the number of accounts into which energy can be stored has to be increased continuously. This basically also translates into our expanding universe. Think of the universe itself as one system. If the universe itself is considered as one system, it is having maximum freedom in its own way, but it is continuously still expanding. What does it mean that it is expanding? It is expanding into something else, meaning it is technically expanding into more accounts where it can store its own energy. So, in a sense, everything which we are doing is continuously allowing the universe to expand. Anything and everything which we are doing is being done. Because it is being done, it is automatically paying a tax to the universe. In a way, we are automatically increasing the entropy of the universe by everything which we do, by everything which happens. Because we are automatically increasing the entropy of the universe, that allows the universe also to expand further and further. Maybe this rule may have been different if our universe was a contracting universe, but we will never know, because we have no data at all, because ours is an expanding universe. And in our universe, one of the universal rules is, if we do not pay a tax to the universe, we are not allowed to do what we are doing. We just don't understand it because we have got so much freedom. We do so many things, but anything and everything which we are doing ultimately is something which is paying a tax to the universe at the end of the day. What is a tax? We are increasing the entropy of the universe if we are doing a process spontaneously. Do you understand the principle over here?
Yes, sir.
This is one of the universal rules which is actually properly a universal hidden rule. Just like light is going to be the highest speed which you can ever achieve, this is another hidden universal rule. We just don't see it as a rule because it is so vast and so we can't even imagine it. Think, anything and everything we do is automatically spontaneous. Regardless of whether it is spontaneous to us or not, it is spontaneous to universe. And if it is spontaneous to universe, it is automatically forcibly doing this. That delta S is going to be positive for the universe. We are automatically increasing our entropy of the universe over here. Alright, so I'll shut up here. There is going to be a bunch of either questions or theory depending on what I have prepared. If I have prepped for questions, I'll probably discuss questions on thermo tomorrow, if standard model, so to say. If I have not prepped for it, I might go for theory for whatever other pieces left over. What time works tomorrow for class, Ra?
Anytime.
Anytime during the day works. How do I make sure I'm connecting with you immediately? Let's say I'm finding some time free. Do I directly give you a call?
Sure, sir.
That'll work?
Yes, sir.
Okay, alright. So what time to what time? Daytime, anytime is okay?
Yes, sir. Daytime, anytime.
Morning from when? 7 के बाद? 6 के बाद?
Yes, sir.
I mean, obviously you will want to sleep in a little bit more. Freedom तो थोड़ा तो utilize करना है. So 6:30 के बाद I'll give you, if I am awake, we can have a class. Is that fair?
Yes, sir.
6:30 plus 6:30 or 7? What do you prefer?
After 7, sir.
After 7. Okay, huh. 7 is not a problem, na?
No, sir.
Okay, alright, cool. After 7 in the morning, any time is free. Alright, cool. Ta-ta-da, bye. Good night. Have a nice night.
Nice, sir. Thank you, sir.